Good day, students. Welcome to another online session for the course Computer Organization. And in this session, we will be discussing about memories, and we are starting chapter number 5. And the title is Large and Fast Exploiting Memory Hierarchy, in which we will going to discuss the hierarchical memory system. What are the benefits of hierarchical memory system, and what are the levels in which the memory is being distributed, and how, if a processor requires any data, then how in a hierarchical memory system the data is being updated to the processor. We will discuss that in detail, and in this chapter we will be focusing on the cache memory or the cache memory, and then the visual memory concept we will also want to discuss that in detail. So coming to the memory technology in our computer system, we know that different types of memories are being used, and each memory has its own significance and importance. For example, we can have the static RAM inside the system, and static RAMs are normally the smaller RAMs but are efficient and faster RAMs as compared to a normal RAM, that is the dynamic RAM. So the normal access time of the static RAMs are zero point 0.5 nanoseconds to 2.5 nanoseconds. We can find out any static RAM in between these configuration, and but the issue is the price element. The price is so much high. It's $2,000 to $5,000, and because it's implemented on a transistor level, and uh, it's implemented on chip. So the cost element is definitely high as compared to the dynamic RAM that are implemented with the help of capacitors. So we can achieve the limited size with static RAM, but the performance element is much more higher as compared to the other components. Now coming to the dynamic RAM basically uses capacitor as the data storage. So these RAMs are slower as compared to the static RAMs, but as far as the cost element and the volumes and the capacity is concerned, we can achieve higher capacity as compared to the static RAM. So normally you can find out a dynamic RAM in between 50 nanoseconds to 70 nanoseconds, and the cost element is from $20 to $75 per gigabyte. So these RAMs are economical, but as far as the speed is concerned, we have to compromise on speed in order to achieve economical solutions, and uh, can achieve the higher volumes in terms of storage. The next are the magnetic disks, and these are definitely the slower as compared to the dynamic RAM. Their access times normally are in between 5 milliseconds to 20 milliseconds, and their cost is definitely slower. That is $0.20 to $2 per gigabyte. And if we consider the idle memory, then access time of static RAM is good, and capacity and cost per gigabyte of the disk definitely are better for the other scenarios. The principle of locality suggests that programs and instructions which we have accessed recently, there is a high probability that in future, in near time, we could reuse them again. So, a program accesses a small portion of their address space at any time, and the locality has been distributed into two categories, which we have discussed in detail while we were discussing the session one portion. One is a temporal locality. If the decision is based on the time, then uh, for example, all those items which are recently accessed, and there is a high probability that they would be accessed again soon. So for example, we've got instructions in a loop and induction variables. That is the example of that have the temporal locality in it, while special locality deals with space elements. So items that are near to each other are likely to be accessed soon. For example, any sequential data access or the accessing of data from the array. This is the example of special locality or special locality. We can say special locality that recently accessed items are going to be accessed soon. So if our system is accessing data on that principle, it could while getting any block or data, it could access all the nearest block, and if those blocks are accessed, then all the time of the processor that is used to access the memory can be saved. Hence, the performance can be increased in that particular way. So we have to take the advantage of the principle of locality. So we use a memory hierarchy basically. So what we used to do is we store everything on the hard disk, and we copy the recently accessed and nearby items disk to the smaller dynamic RAM memory. That is basically your RAM or the main memory. And we copy more recently accessed and nearby items from dynamic RAM to smaller static RAM, that is the cache memory, or the cache memory that is attached to the CPU. So the level, if we consider the level, we've got a CPU, and inside the CPU we've got registers. Then we've got the cache memory. Then we've got the RAM, and then we've got the hard disk drive. This is the hierarchy that is maintained in the hierarchical memory system. So if any block or any data can be accessed from the cache memory, then the CPU can save a lot of time. But if the same block can be accessed from the hard disk drive, the lot of time is wasted since the CPU is the fastest device, and that requires data at certain rate. So as we move away from the CPU, the devices get slower, but we can achieve the capacity. As we move closer to the CPU, the devices, the storage elements get faster. For example, cache memory is much efficient as compared to the RAM, and RAM is much efficient as compared to the hard disk drive. So how the memory hierarchical levels are being used basically, if you consider that the smallest unit which we can move from one memory to another is basically known to be a block. So the unit of copying is known to be a block, or we can call it a line, and we can have a multiple blocks here. If you see that we have got a processor here, this is the cache memory for example, and this is the RAM. So what processor used to do is processor used to access the level that is nearest to him to it. Basically, processor will gonna see the required block in cache memory, and if that block is found in a cache memory, it is called a hit. So the hit is basically all those references that are found in the cache that are known to be the cache hit. So you don't have any sort of penalty in terms of clock cycles in terms of hit, because you don't have to access RAM for those particular blocks. No cycles are wasted in that particular scenario. But if that block is not found, then we'll move to the immediate level, that is, for example, the RAM, and we'll move that block from RAM to cache in the processor. So if the data is accessed which is used to be accessed is present at the upper level, that is called the hit. And hit ratio is basically the number of hits per accesses, that is known to be the hit ratio. And if the data is not present in the upper level, for example the cache memory, that is called a miss. Then we copy the block from the lower level, and time taken to copy the block from the lower level to the upper level, that is the miss penalty. And the ratio is of miss ratio is basically 1 minus hit ratio is known to be the miss ratio, or hit rate you can say, or miss rate. Okay, so this is the way the processor used to access the block either in a cache memory or the RAM. So if you consider the cache memory, the level of memory hierarchy closest to the CPU, that is the cache memory. So it acts as a buffer storage or temporary storage, because the cache memories are faster as compared to the RAM. So any blocks if can be found in the cache memory, uh, the processor time to access the RAM is saved basically, and our system performance is improved. So, for example, we've got the following accesses x1 till xn. So, before xn, that block was not present in the cache. So, uh, how do we know that that block is present in the cache or not? So, we should have the block identification strategy that could identify the block, either the block is present in the cache or not. And if the block is not in the cache, then we have to move that block into the cache so that we can access that. The processor can access that in near future if again the reference is required for that particular block. Now, as far as the block identification is concerned, we've got three orientations of the cache memory. Either the cache memory can be direct map, either the memory can be set associative, or the cache memory can be fully associative. So these are the three distinct categories depending upon the identification of the block, and depending upon the block identification, we can distribute the cache depending upon the physical orientation into the three categories: that the direct map cache, the set associative cache, and we will discuss those cache memories also: set associative and fully associative. In the direct map cache, we've got one-to-one correspondence of the blocks with the RAM. So each block can be placed in a specific location, and the mapping is one-to-one. How we're gonna know that which block maps to the which location of the cache? The simple method is we have to divide the block address with the number of blocks in the cache, and the reminder basically tells us the location in which we can see that that block can reside. So there is another way that blocks are definitely are in the power of 2, and we can use the lower order address bit to identify which block will reside and at which location. So in this particular example, you can see that this is the cache memory, this is the cache memory, and this is RAM. And cache memory consists of 8 locations or the 8 blocks. So either we can use the lower order bits to identify which blocks maps to which location, or either we can divide the block address with the number of blocks in a cache and see the reminder bit, or we can use the mod operator basically. So this is the modulo operator that returns the reminder basically to identify which location is used to store that particular block. Now, how are we going to identify that that block is valid or not, or that particular block is stored in a cache or not? So we've got some block identification strategy, and block identification strategy tells us that the block address basically has been distributed into three categories. So we've got the tag bits, we've got the index bits, and we've got the offset bits. That distribution basically is used to identify the block along with the valid bit. So we store the block address as well as the data basically. So actually we need the higher order bits called the tag bits. We also store the tag while storing the data of that particular block, and we also set a single bit that identifies in the cache that the block is valid or not. So we've got a valid bit. So if valid bit is equal to 1, so the block is present and valid, and 0, that means the block is not present. So initially the cache memories are all the locations have the valid bit equals to 0. So consider the following particular example in which we've got 8 blocks in a cache. So 8 blocks can be represented in 3 bits. So these are the index bits that are 3 bits from the block address starting from 000 till 111. The valid bit is set to 0 for all the locations because the cache is initially empty. There is no tag stored, there is no data stored in this particular example, and we will move forward and we will see how the data is being stored in the cache memory. Now the word address that the processor requires is 22. So we have to convert that into the binary basically. This is the binary, and if you see that the index that has been selected here is 110. The lower order bits in address bit, that is are the index bits. Or you can also use that formula, the block address modulo number of blocks in a cache, to find out the location, which means that the word the block at word address 22 would store at this particular location. We move that location from a block from RAM to memory, and we set the valid bit to 1. This is the tag bit. We store the tag and we store the data on that particular location. So for the first access, it was miss. It was the cache miss because the cache memory was initially empty, and we have to move that block to the cache memory. And for the next time, if that block is again required, then definitely that block would be hit in the cache memory. Now we've got a word address 26. That is also a miss because that was not present, and it would store at 010 index basically, and the tag is 11 basically. So we set the valid bit to 1, move the data to the location, and store the tag as well. Then again, there was a request of 22 and 26. Since these blocks are already present in the cache memory, they are also valid. Their tags also match, so they contribute to hit. So in that particular scenario, we don't have to go to the RAM in order to access these two blocks. Now coming to two another blocks that are 3 and 16, that are basically the miss basically because they were not present in the cache memory. And then again 16 was again accessed, so it's once it's moved to the cache memory, then it's a hit. Now coming to the word address 18 basically, so we came to the specific index, and if the tag is not matched, and if we have some already data that is been stored here, we have to replace that data. It's a miss basically, and we have to move that block into that particular location. Well, that was all for today's discussion. In the next session, we will be discussing the address subdivision, how the block address has been distributed, and how the hit and the miss is generated. We will discuss that structure in detail. Till now, have a good day. Take care.